Hi there, Miss Barber here. This lesson is titled Limits at Infinity, Horizontal Asymptotes. To explore these concepts, we are going to consider the graph of the function y equals arctan of x. As we observe this graph, let's note that as x approaches infinity, the graph itself, while increasing, approaches some upper bound, a horizontal line. That line that it approaches is called the horizontal asymptote, and we denote that as y equals pi over 2. As x gets larger, g of x gets closer to the value of pi over 2. In other words, we say as x approaches infinity, g of x approaches pi over 2, and the limit notation we write as the limit with x right arrow infinity below the limit of g of x equals pi over 2. Similarly, let's study the graph as x approaches negative infinity. As x gets smaller and smaller and smaller, the graph itself approaches a lower bound that looks like y equals negative pi over 2. We call that the horizontal asymptote, y equals negative pi over 2. Similarly, we say that the limit as x approaches negative infinity of g of x is equal to the negative of pi over 2. Notice that what the limits approach as x approaches plus or minus infinity gives us the equation of the horizontal line, which is the horizontal asymptote. Let's look at some theorems. We'll start with the definition. If either the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L, where L is a real number, then we say that the line y equals L is a horizontal asymptote of the graph y equals f of x. Let's learn this theorem. Suppose n is a positive integer. Bullet point 1. The limit as x approaches infinity of x to the n equals infinity. What does that mean? If you have big over small, so big would be x to some power, over small could be the constant 1, then that limit will approach infinity. Now the second bullet point. The limit as x approaches infinity of x to the minus n. That equals 0. Let's see why. We can rewrite that limit as the limit as x approaches infinity of 1 over x to the n. And that is if you have a small number divided by a big number, it eventually approaches 0. And finally, the third bullet point of the theorem. The limit as x approaches negative infinity of x to the n is equal to, and notice this is piecewise defined, that limit equals infinity if the power n is even, and it equals negative infinity if the power n is odd. Also note that the limit as x approaches negative infinity of x to the minus n is equal to 0. Example, find any horizontal asymptotes of f of x equals 9 minus 7 over x to the 4th plus 4 divided by x to the 6th. To find horizontal asymptotes, we find the limit as x approaches infinity of the function. That means we want the limit as x approaches infinity of 9 minus 7 divided by x to the 4th plus 4 divided by x to the 6th. Let's take each of these limits separately. That is, let's write this as the limit as x approaches infinity of 9 minus the limit as x approaches infinity of 7 divided by x to the 4th plus the limit as x approaches infinity of 4 divided by x to the 6th. For the first one, the limit as x approaches infinity of 9. 9 is a constant. It will not be affected here, so that will just be 9. To find the next two limits, let's recall from the theorem where we learned that the limit as x approaches infinity of 1 over x to the n equals 0. Applying that theorem, then the limit as x approaches infinity of 7 divided by x to the fourth is 0, and the limit as x approaches infinity of 4 divided by x to the sixth is also 0. Thus we get that the limit as x approaches infinity of f of x equals 9. That satisfies our definition of a horizontal asymptote. Our horizontal asymptote is the line y equals 9. Example, find the limit as x approaches infinity of 100x squared minus x, all divided by 3x to the fifth minus 6x squared plus 1. When we take the initial limit, we end up with infinity over infinity, and that means that's an indeterminate form. So we need to do something else. For problems like this, we divide each term by x to the highest degree present. The highest degree present is x to the fifth. So we'll write the limit as x approaches infinity of 100x squared divided by the highest degree present would be x to the fifth minus x divided by the highest degree present is x to the fifth. That's for the numerator. And then for the denominator, we'll have 3x to the fifth divided by the highest degree present, which is x to the fifth, minus 6x squared divided by the highest degree present, which is x to the fifth, and then plus 1 divided by the highest degree present, which is still x to the fifth. Let's simplify some of the exponents. This will give us the limit as x approaches infinity of, and for 100x squared divided by x to the fifth, using rules of exponents, it's 100 over x cubed. Then we have minus x divided by x to the fifth, using rules of exponents, would be 1 divided by x to the fourth. Let's continue to simplify the exponents in the denominator. 3x to the fifth divided by x to the fifth leaves us a constant of 3, minus 6x squared divided by x to the fifth. That's 6 divided by x cubed, and the last term we leave alone as 1 divided by x to the fifth. Now we will take the limits and remember the property or the theorem that we learned, which stated the limit as x goes to infinity of 1 over x to the n goes to 0. We will apply that theorem to the limit as x approaches infinity of 100 over x cubed. That's 0. And we'll apply that theorem to 1 over x to the fourth as well. That'll give us 0. The 3 is a constant, stays put, minus the limit as x approaches infinity of 6 over x cubed. That'll go to 0 because the denominator gets real big. Similarly, for the limit as x approaches infinity of 1 over x to the fifth. That will also go to 0. 0 minus 0 in the numerator is 0. In the denominator, 3 minus 0 plus 0 is still 3. 0 over 3 is 0. So we see that the limit as x approaches infinity of our function equals 0. If we were looking for the horizontal asymptote, we would say that the horizontal asymptote is the line y equals 0, which is the x-axis. In general, consider a rational function, which is a quotient of polynomials. You could write that as f of x equals p of x over q of x. Let's say that the degree of p of x, the numerator, is the power of the leading coefficient, and the degree of the denominator, that's of q of x, is also the power of the leading coefficient. Leading coefficient is the term with the highest degree present. Let's divide the numerator and the denominator by x to the power of m. That's the degree of the denominator. After you perform the algebra, that complicated looking complex fraction reduces to a sub n, which is the leading coefficient of the numerator, divided by b sub n, which is the leading coefficient of the denominator, times the limit as x approaches plus or minus infinity of x to the n minus m. The whole purpose of this algebra exercise is to show that only the lead, that's the highest degree coefficients, only the leading coefficients are relevant when looking for horizontal asymptotes. Example. This is called the cases, and we're going to look at 3 different cases that can happen between the degree of the numerator and the degree of the denominator. If you have a quotient, p of x divided by q of x, we will refer to the degree of the numerator as the power of n, and we will refer to the degree of the denominator as the power m. Let's consider the case first in which the degree of the numerator and the degree of the denominator are the same. We divide by the highest degree present, so we take the limit as x approaches negative infinity of the highest degree present is x to the 4th. So you'll have 3x to the 4th divided by x to the 4th minus 7x divided by x to the 4th plus 9 divided by x to the 4th. Let's do this term by term division for every term of the denominator as well. So now you'll have 7x to the 4th divided by x to the 4th minus 4 divided by x to the 4th. Let's simplify using rules of exponents. This will give us the limit as x approaches infinity of, and in the numerator, the x to the 4ths cancel, so you have 3 minus 7, 1x in the numerator, 4, that's x to the 4 in the denominator, so you would end up dividing that by x cubed. And for the last term, the 9 over x to the 4th stays put. Let's finish the division. In the denominator, 7x to the 4th divided by x to the 4th is 7. And the second term stays put. 4 divided by x to the 4th. We're going to use the theorem we learned previously, that is the limit as x approaches infinity of 1 over x to the n goes to 0. We have the limit as x approaches infinity of 7 divided by x to the 3. This goes to 0. Similarly, for 9 divided by x to the 4th, as x approaches infinity, that term goes to 0. And in the denominator, the limit as x approaches infinity of 7. The 7 is not affected because it's a constant, but a 4 divided by x to the 4th, that'll go to 0. So when you finish, we end up with 3/7. This function has a horizontal asymptote of the line y equals the constant 3/7. Let's look at the case where n is less than m. So we are looking at a rational function, p of x divided by q of x, where the degree of the numerator is n and the degree of the denominator is m. For this limit as x approaches infinity of 3x cubed minus 7x plus 9 divided by 7x to the fourth minus 4. Notice that the degree of the numerator n is 3 and the degree of the denominator m is 4. We'll do the same process as in the previous case, and that is we're going to divide by the highest degree present, which would be x to the fourth. So let's write the limit as x approaches infinity of 3x cubed divided by the highest degree present is x to the fourth minus 7x divided by the highest degree present is x to the fourth plus 9, again divided by x to the fourth. We'll do this again for each term in the denominator. So you'll have 7x to the fourth divided by x to the fourth minus 4 divided by x to the fourth. Now we will apply the theorem that we previously learned, which is the limit as x approaches infinity of 1 over x to the n is 0. How does that help here? Let's simplify first. We could write this as the limit as x approaches infinity of, and in the numerator we'll have 3 over x minus 7 over x cubed plus 9 divided by x to the fourth. All of that divided by, and in the denominator, you got the x to the fourth divided by x to the fourth, leaving you just the 7, minus 4 divided by x to the fourth. Now let's apply that theorem. Each of the terms in the numerator go to 0. And the one term, 4 over x to the fourth as x approaches infinity, goes to 0 as well. The limit solves to 0 over 7, which would just be 0. Thus, the horizontal asymptote is the line y equals 0. Now let's look at the third case. For the rational function f of x equals the numerator p of x divided by the denominator q of x, the numerator's degree is n, the denominator's degree is m. In this example, the case is where the degree of the numerator is greater than the degree of the denominator. We have the limit as x approaches infinity of 3x to the fifth minus 7x plus 9 divided by the quantity 7x to the fourth minus 4. Let's divide each term by the highest degree present. Here the highest degree present is x to the fifth. We will have the limit as x approaches infinity of 3x to the fifth divided by x to the fifth minus 7x divided by x to the fifth plus 9 divided by x to the fifth. That's term by term division for every term in the numerator. Got to do this again for every term of the denominator. So we'll have 7x to the fourth divided by x to the fifth minus 4 divided by x to the fifth. Let's use some properties of exponents and simplify this a little bit. We can write this as the limit as x approaches infinity of the numerator, x to the fifth divided by x to the fifth becomes a factor of 1. So you got 3 minus 7x divided by x to the fifth would be x to the fourth plus 9 over x to the fifth. And in the denominator, we will have 7 and 1x remaining in the denominator of the denominator minus 4 divided by x to the fifth. Look what happens. The numerator, 2 of these terms go to 0, and in the denominator, both of the terms go to 0. So you have 3 divided by 0, which can't happen. This actually means the limit goes to infinity, and so we conclude no horizontal asymptote. Evaluate the limit as x approaches negative infinity of negative 4x to the 6th plus 2x cubed plus 7. We're approaching infinity, positive or negative is irrelevant, and so we want the extreme behavior. That means we're only concerned with the highest degree present when solving for the limit. So this limit would be exactly the same as solving for the limit as x approaches negative infinity of the highest degree, which is negative 4x to the 6th. Let's compute that. That would be negative 4. And then I'll put in negative infinity to the 6th, but keep in mind that you really cannot raise infinity to a power. I'm primarily concerned with the SIGN. A negative infinity raised to the 6th, that's to an even power, makes it positive. So you got that positive infinity times a negative 4. While the 4 is inconsequential, the negative is not. This gives us negative infinity. By the way, this coincides with your previous algebra knowledge. For example, if you were wanting to graph the end behavior of f of x equals negative 4x to the 6th plus 2x cubed plus 7, on a coordinate plane, the highest degree being even means both endpoints face the same direction, and negative would mean both endpoints face down. And so if we take the limit as x approaches negative infinity, we see that the function itself also approaches negative infinity. Example, evaluate the limit as x approaches infinity of negative 10x plus 6 divided by, and in the denominator x plus, under the square root, 16x squared plus x to the minus 1 plus 3x to the minus 2. If we were to compute this directly, you'd get infinity over infinity, which doesn't give you any information. This is an indeterminate form. So we need to do something else, and we're going to do some clever algebra. Before I proceed, let me just point out the obvious. That is, if I have the square root of x squared, you agree that that's x? Just keep that in mind, and we'll continue. What I'm going to do next for this problem is write it again with no negative exponents, because that makes it a little bit cumbersome to see. So I'll write the limit as x approaches infinity. The negative 10x plus 6 we're cool with. The x in the denominator we're cool with. But for the stuff that's under the square root, the 16x squared we'll leave alone, but x to the minus 1, let's write that as 1 over x. And we have plus 3 x to the minus 2, we'll write that as 3 over x squared. What we're going to do next is what we've done in all previous examples, and that is divide each term by the highest degree present. Here, the highest degree present is x, because the square root of x squared is x. Let's write this out. This will be the limit as x approaches infinity of, and we'll write negative 10x divided by x plus 6 divided by x. Let's be very careful with the terms in the denominator. The x is there, but we need to divide that by the highest degree present, which is x. Now, we're going to have plus under the square root, 16x squared. But if you put x under a square root, then that actually becomes x squared. The square root of x squared is x. Then we'll have plus 1 divided by, and because an x is already there, it'll be x cubed, plus 3 divided by, since x squared is already there, this will be x to the 4th. Let's simplify those exponents, and this becomes the limit as x approaches infinity of, in the numerator, the x's cancel, you get minus 10, plus the 6 over x stays put. In the denominator, the x over x becomes 1, plus, let's be very careful with the terms under the square root. X squared divided by x squared is 16. And we'll just copy the 1 over x cubed plus 3 over x to the 4th. Now take the limit. That means we're going to let x get real big. And so if you have a small number like 6 divided by a real big number because it's approaching infinity, that'll go to 0. Similarly for 1 over x cubed and for 3 over x to the 4th. So now that we've taken the limit, in the numerator, you'll have negative 10, and in the denominator, 1 plus the square root of 16, negative 10, and the square root of 16 is 4. Add that to 1 is 5. And look at that very complicated looking expression. The limit as x approaches infinity goes to negative 2. It means that expression has a horizontal asymptote of negative 2.